Hello, everyone. In this video, we will give a guide and tips for chapter 29 of my Java book. Chapter 21 is on weighted graphs and applications. The preceding chapter is on unweighted graphs and applications. For the weighted graph, we're going to add weights on edges. So here is US map. So now we have an edge between the two vertices, Seattle and Chicago. So here's the weight on the edge representing the distance between the two cities. So now you can ask this question, what is the shortest path from Seattle to Miami? We can solve the problem and using the weighted graph algorithms. In this chapter, we're going to look at how you represent a weighted graph and how you model weighted graph and design a weighted graph class and implement the minimum spanning tree and the shortest path algorithms. All right, so representing weighted graph, what we need is this. So there are different ways you can represent graph, but the most convenient way is we're going to use this weighted edge. So weighted edge extends the edge. We're going to add additional property is the weight on the edge. And also we're going to make this weighted edge comparable. So this is the comparable, and so you can compare two edges by their weights. So this is needed for the weighted graph applications. You need to finding the shortest path, the minimum spanning tree. So we have to do this kind of comparison. And we're going to store all this information, the adjacency edge list. So here is the neighbors bracket 0. So you have this is 0, 1, that's the edge, and that's the weight. And this is 0, 3, and the weight is 8. So this is in the weighted edge object. And now we have this weighted graph class, and which is subtype of unweighted graph, and so which is also a subtype of the graph interface. So you have all this. Now you have the methods inherited from unweighted graph. Additionally, we're going to overwrite this. We add the additional method. Here's the get weight and add age, weighted age. So this is the minimum spanning tree. This is the shortest path. So here is the complete implementation of this weighted graph class, and this is a test program that uses the weighted graph class. Okay, now, so here's the minimum spanning tree. So what is a minimum spanning tree? It's a tree that consists of all vertices in the graph. So it is a tree. So not all the edges. We're going to get all the only part of the edges from the graph. So the result is in the minimum spanning tree. So you connect all the vertices. So this is minimum spanning. This is the spanning tree. So there are a lot of spanning trees, and the total weight is 42, and this is total weight is 38. This is total weight is 38.2. Now it turns out, and for the minimum spanning tree, the total weight is 38. So it's not unique. You can see you can get a C and D both are fine. So here's the algorithm for finding the minimum spanning tree. So we use the this greedy algorithm to find the minimum spanning tree. So this is initially the minimum spanning tree is empty. So you keep bringing vertices into this. And now which one you're going to add? You're going to add the one and that has the minimum age among all these possibilities. So you add it into this right here. So moving, it's right here. So, and we use this illustration and to demonstrate the algorithm. And now we refine the Prim's algorithm using this cost. So this is the animation for this refined Prim's algorithm. So here's the implementation. And so minimum spanning tree returns a tree, the minimum spanning tree. So this is the minimum spanning tree. It's a subtype of search tree. So it is a tree, so that's returned. Here's the test code and using this method, minimum spanning tree. Next, we look at the algorithm for finding the shortest path. So this is the algorithm, is the Custer's algorithm. It's actually, you're going to find the shortest path to all the vertices from a single source. That's, you want to find the shortest path between two vertices, but the byproduct of this algorithm is that you find the shortest path from one source to all the vertices. So what it does is, so you have, this is the source here, S. So initially you put an S there, and then you keep adding the vertices here. So which one you're going to add? You add the one which has the minimum cost. The minimum cost is this, the cost is defined as the distance from the vertex to the source. So this is the shortest path algorithm. So we get the shortest path tree from shortest path, get shortest path method. So which is subtype of, actually, this is the we need to change this. It's the search tree. It's this. So we have this, everything here. All right, so that is all for this shortest path. And the next is a case study on weighted nine-tail problem. In the preceding chapter, we have the nine-tail problem. So in that, we just look at the number of flips. So now we're going to add weights. So when you flip something, you're going to consider all this adjacent. So when you flip like this H, you're going to flip H and also its neighbors. So this is 3 times. So we're going to add this as a weights. So that's the total number of flips. So this is going to be, the problem is we're going to find the minimum number of flips to flip a pattern into all tails. And so this is starting pattern, you have some heads, and we want to get everything into a tail. So that is the weighted nine-tail problem. That is all for a summary of this chapter on weighted graphs and applications. Thank you for watching. Goodbye.